Hello, my name is Bezryadina. I'm from California State University of Northridge, and I will talk today about nonlinear self-trapping and guiding of light in biological suspensions. Deep penetration of light through scattering media is important because it may improve many areas in biological light-matter interaction, especially deep tissue radiation for medical treatments. To understand these waveguides, we must understand the optical forces involved, polarizability and tunable nonlinearity, also how the suspended particles are transported through the solution and how they can be manipulated. Knowing these effects, we can use them to develop soft matter system with engineered nonlinearity and maybe even biodegradable nanotechnology in the future. Light propagation and linear effects have been studied before with dielectric suspensions. Several research groups demonstrated solitons formation from tunable polarizability and self-induced transparency effect in the suspensions. Today, I will discuss biological suspensions, nonlinear trapping versus scattering in the suspensions, how to create waveguides in cyanobacteria and red blood cells without damaging the cells. The waveguide depends on the wavelengths. What happened when we tried to use nonlinear coupling with biological waveguides, and finally, what happened with complex structured light in the biological suspensions. Before we'll go through this, let's introduce a couple important concepts. First one, what I'm using as a word soliton or self-trapped beam. Normally, when we shine light, light diffracts in linear regime. However, if we have a nonlinear media or we have a nonlinear effects, we observe self-focusing. If we can find a balance between normal diffraction and nonlinear self-focusing, we can create this soliton or spatial soliton beam, which will propagate with the same shape over a long distance. Second concept is important optical forces in suspensions. All biological particles, almost all of them, are positive polarizability particles. This implies that index of refraction of the particles is bigger than index of refraction of the surrounding media. That implies that particle will get attracted toward the center of the laser beam. When we talk about optical forces in suspensions, we have two forces. Gradient forces. It's a force which is proportional to the gradient of intensity. Then it's happened because the intensity is greatest at the center of the beam, which pulls particle toward the center of the beam. And it's create a high index of refraction at the beam center along the direction of propagation of the beam. Second one is forward scattering force, which is proportional to the intensity of the beam. It's created by light scattered off the surface of the particle, and it propels particles forward along the direction of light propagation. The setup to create a single beam waveguide is quite simple. Here the illustration of it. We have continuous wavelength laser beam. Here's a green laser beam. We collimated it and we focus it just inside of our sample. Usually we have 3 to 5 centimeter long cuvettes with a sample. Using cameras, we can monitor the beam profile from the side along the z-axis and from with profile camera at the exit face of the cuvette. The first biological waveguides were created in cyanobacteria suspensions, propagating through several centimeters of the media. Here is animation of it, how bacteria are drawn inward and forward by light beam and creating a waveguide. This work was featured in Optics Photonics in 2017. Okay. Now let's look quickly what's happening. This is a very common bacteria. They're very small, 2 micrometers long. They live in seawaters pretty much everywhere in our planet. And if we send laser beam just in seawater without bacteria, light normally diffracts, even at high laser power. However, if we introduce bacteria, we obviously observe strong scattering. When we increase laser power, nonlinear effects start to play, which is quite surprising because bacteria have a very close index refraction to the media, but we see still strong nonlinear effects and we create beautiful waveguides. So self-guided waveguides created in biological media without critical damage at low absorbing wavelengths. We did viability assessment and we show that mortality rate is less than 0.1%. Before we have exponential model which take account of the optical gradient forces, and this model could not explain why we can create biological waveguides. Roberto Marandotti group in Canada proposed a completely new model, forward scattering model, which take account optical gradient forces along with forward scattering forces. With these models, what we observe that particles get attracted toward the center of the beam, and then they push forward. Okay, here's again the video of it. The back particle get attracted and push forward. And when we apply this model to our simulations, we created results with the similar parameters, which corresponds to our experimental results. We can create biological waveguides not only with the small 2-micron particles. We observe waveguides with red blood cell suspensions. This work was done with human red blood cells, and we create several centimeters long waveguides, and it was featured in Optics Photonics in 2019. In follow-up work, we use sheep red blood cells, which are slightly smaller than human red blood cells. They 4 to 5 micrometers in diameter, but they also have a disc shape. So what we will look how do these waveguides work at different wavelengths. Before we create them only in a green light, what happened with different wavelengths? It's important because if we want to use it for biological application, we want to increase the range of wavelengths which we can use. So this is our experimental setup. We introduce couple more lasers, we collimate them, and then we co-align them all directly one on top of each other, and they all focus in the beginning of the cuvette, and we have same 2 cameras. We take an account with our imaging system for difference in optical path for different wavelengths, and also we introduce a filter so we can look in each of these laser individually. So let's look at the results. If you look on a media where our blood swim without any blood, light diffracts normally, there is no scattering, even at high power. As we increase laser power, as we introduce red blood cells, even at low power, we see linear diffraction and scattering, you can see here. And here in the bottom row, we increase the power and see the minimum output diameter achieved through nonlinear self-trapping just before thermal rings begin to dominate. Our experimental show not all wavelengths are equally guidable. In each case, we see nonlinear focusing at high power. However, infrared light requires much more power than 532. So at low power, we don't see anything. As we increase power, we see waveguides. But near infrared require more power. There are also 2 special cases, 730 nanometers, where weak nonlinear effects lead to weak nonlinear focusing of the beam, and then 170, where thermal effects dominate at low input power. The possible explanation for our weak nonlinear focusing at 730 could be due to strong effect of resonance of trapping forces. Alex Stilgoy from Halin Rubinstein and Loop groups show that the trapping force of Me particles strongly fluctuates with particle size and trapping wavelength. For the second case, 970 is well into water absorption band, leading to strong heating effects at low power, evidenced by these thermal rings. We even observe this heating effect at 930 nanometers, around 1000 milliwatt laser power, which prevent us from reaching the power required to focus as strong as lower infrared wavelengths. Okay, now, can we guide near-infrared laser beam at low power? Do we really need to have such a high power of laser beam to guide through our suspensions? To find the answer for this, we look on a work which was done by Zhegan Chen groups, where they looked on pump probe guiding and metallic nanosuspensions. They create a waveguide with green laser beam in metallic suspensions with gold nanospheres, and then they shine a near-infrared laser beam at low power, and by itself, it's diffract, but when it's coupled to these green waveguides, it propagates through, and we see this guiding at low power. So we use this idea and apply it for our red blood cell suspensions. This is our waveguide of green laser beam at 550 milliwatt power, and you can see it's beautiful waveguide. And now we looked on different laser beams at low power. It's 100 milliwatt alone, and by themselves they could not create waveguides, and you can see they just scattered and there is nothing observed. However, if we send them through our foreign waveguide by green laser, so we have a spam probe coupling, so this guide through this green waveguide, we can see this wavelength nicely and beautifully guide through. Okay, even at low power by itself, but they are guided by the green laser beam. To show how coupling alignments affects the probe beam, here we sweep the probe beam up and down as the palm beam is held stationary. As the light passes the waveguide, we see the great intensity in the center as more light is guided by the palm beam. We also see the output beam diameter of unguided light surrounding the guided beam does not change. This example clearly shows that we have optical force-induced waveguiding. Now, for complex deep tissue imaging and information transmission, the complex structured light with large bandwidth of information need to be sent and preserved through the biological media. So we want to study the conservation of polarization and orbital angular momentum through the SHIP red blood cell suspensions for multiple wavelengths. So what is the light with orbital angular momentum? So compared to regular Gaussian beams, it has a helical wavefront, and it could have a multiple integer level of topological charges, depends on a phase shift. And if you look at its intensity profile, it's look like a donut with nothing in the middle. We have a singularity in the center, and this type of beams carry orbital angular momentum. To detect vortex beams, we need to use Michael's interferometer. Is one of the easiest way to do. We can interfere plane wave with a vortex beam, and in the point of singularity, we observe this fork pattern. You can see this extra line. And if we see this fork pattern, it implies that we have a singularity and we have orbital angular momentum. So this is our experimental setup to study conservation of orbital momentum. We have these two lasers, and we introduced two vortex plates for each of the beams. And before this plates, we got part of the beam which we can interfere after it goes through the sample, so we can look on interference pattern and observe if it has any orbital angular momentum after it propagates through the media. So let's look at our results. So in PBS solution, the vortex beam diffracts normally with singularity preserved at the center. And red blood cell suspensions for low laser power, the vortex beam expands due to the scattering, and vortex beam do maintain the orbital angular momentum after several centimeters of propagation. As the laser power increased to optimal conditions, which is 500 milliwatt for green laser beam and 130 milliwatt for near-infrared laser beam, the donut intensity pattern is more defined with nonlinear self-focusing, reducing the beam outer diameter and expanding the inner diameter. So we create this nice, beautiful donut, and the beam power is confined to a smaller beam area. And if you look at the interference pattern, we can clearly see the fork, so orbital angular momentum is preserved. The light-induced refractive interchange in red blood cell suspensions stabilizes the structured light beam, and the stability of vortex waveguides is determined by the degree of non-local nullarity, which decreases instability and thereby increases the length of stable propagated waveguide. Now, let's look on complex beams guiding through the waveguide. So we looked on different types of fan beams, Gaussian beam or vortex beams, and different probe beams which will guide through this waveguide created by the green beam. We already did Gaussian beams before, and we studied with multiple lasers, so we'll do other combinations. So what we did first, we create a waveguide with our green beam, with Gaussian beam. It's create a nice waveguide, long one, and then we send vortex probe beam at low power, and at low power, it's by itself, it diffracts But as it goes through the green waveguides, it creates this beautiful waveguide. It creates this donut shape, and you can see that orbital angular momentum preserved. Second case, vortex guiding vortex. So we create vortex pump beam. So we create a vortex pump waveguide, and then we send a vortex probe beam, and it's also beautifully guide through an orbital angular momentum preserved. Finally, we create vortex pump beam, this donut shape, like structure goes through, and then we send a Gaussian beam, and Gaussian beam guided through this donut shape waveguide. And there is only one thing, that our beam slightly shift to the side, which makes sense, because if we have any instability of our alignment, our beam shifted to the highest index of refraction, to the highest intensity of the pump beam, which is side of the pump beam. And Gaussian beam doesn't have any orbital momentum, which makes sense. So both vortex and Gaussian beams are capable of nonlinear coupling into the waveguide channel and preserve its intensity distribution and orbital angular momentum properties. Finally, let's look on conservation of polarization states. Here, we introduce polarizers in combination of half-wave plates and quarter-wave plates, which could be flipped in and out. And after the sample, we also introduce polarizers, analyzer, and quarter-wave plates, so we can observe how the polarization change if we have any shift of polarization as it goes through the suspension. We checked linear polarized light, vertical and horizontal. We checked a right circular polarized and left circular polarized beam, and for all of them, we didn't observe phase shift in polarization for circular and linear polarized light. The polarization red blood cell suspension has less than 0.1 degree of polarization rotation compared to rotation of polarization in the media by itself. In summary, we created biological waveguides in suspensions with non-significant damage. We studied wavelength dependence in waveguide formation. We showed pump-probe coupling in biological media, demonstrated the conservation of polarization state and orbital angular momentum. And our future work is focused on developing soft matter system with engineered nonlinearities and biodegradable nanotechnology. I want to acknowledge everyone who worked on this project, Zhigan Chen Group at San Francisco State University, NRS Group in Canada under Professor Roberto Morandotti, and Tobias and Benjamin, who are professors themselves at different universities right now. They did theoretical work. Daryl Priest at University of California, Irvine, and my student Nicholas Perez, who did all late work on ship red blood cells. Thank you.